Okay, this is a AS review for all the mechanics chapters because they can all be interlinked and jumbled up, kind of. Okay, so instead of giving you the normal format, okay, I am going to try to change things up a bit to provide a slightly different perspective about mechanics. Not that it's a different thing lah. Okay, so I'm going to start from the middle. Okay. So in mechanics, right, it may seem that we concern ourselves with force, but actually what we actually concern ourselves is changes. And the first change that we will look at is the change in velocity. Because when there is a change in velocity, a few things happen at the same time. On one side, there is a acceleration. And from the acceleration perspective, right, there will be uniform and non-uniform acceleration. Most of the calculation that you have is in the uniform region because this is where kinematics is what. Whenever there's a change in velocity, we know that there's acceleration and then there's uniform acceleration, which normally breaks down into any form of car driving on the road, car seeing a sign and then emergency brake. So normally this will involve graphing or your 4-Ch2-5 equation. Okay, hopefully you remember and know how to use them. List out the Ch2-5. Okay, and also goes without saying that we will then apply this. The application is on free fall, classical either graphing. So I will call this linear motion in stages. It can be anything, okay? Linear motion in stages. It can be free fall. It can be projectile. Projectile is actually 2-dimension free fall. So the extra tools that you need to do to deal with this, right? Besides knowing the 4-Ch2-5 equations, okay, is also to know how to determine the relationship between the graphs. Because when you think about the graph, right, you will have your displacement time, velocity time, and acceleration time. But my friends, the x-axis doesn't always have to be time. It can be distance, as you will see in while you do past year questions. It can be distance traveled. I think that's the only variation lah. Okay, so normally we look at this gradient to be equal to velocity. Okay, and this gradient is equal to acceleration. Why? Because of definition. So obviously you should know the definition of displacement and velocity and acceleration. So I'm going to just add more space and write the definition up here. Velocity, always use calculus. Rate of change of displacement. Okay, so I'm sorry if you do physics and you're not familiar or with maths. It's just a bit harder for you lah, but we are still going to write it as rate of change of velocity. Okay, so we look at this. That's why we look at the gradient. Because from here, your V is equal to ds dt, and your A is equal to dv dt. And if you remember, we use this in our simple harmonic motion or oscillation if you've studied A2. Of course, we can reverse back. So this area is equal to displacement as well. Okay, so being able to get information from the graph and or use your Ch2-5 equation is important. But for projectile, right, and 2D free fall, this one you need to understand resolution of vectors. So your free fall got X direction, got Y direction. So you can see how we can combine chapter 1 together with this chapter. Okay. Next thing, free fall. For free fall, we sometimes will fall under the non-uniform acceleration portion. Okay, this one we need to talk about drag force. So in my brain, all this is in the same family lah. But it is also kind of related to the other branch of change in velocity, which is change in momentum, which will lead to forces. So whenever there is a non-uniform acceleration, we will have drag force. Drag force or air resistance or viscous force. So if let's say you are just the type where you don't feel a lot with English, then writing out all the names will help you lah, so you don't get thrown off the bat like, wait, why got this one? So non-uniform will involve all these resistive forces. These are all within the class of resistive forces. But if you have done enough past years, especially the objective, there's that one question or one type of question that also includes into the non-uniform force upthrust or your buoyant force. So let's say you have an object falling down. Okay, so depending on where the object is falling down, is it falling down in the beaker of oil? Is it falling down through air? There's number one, always weight, mg. But also at the same time, there is drag force. I'm just going to label this one as D. And there's maybe, depending on factors like volume of the object and also the density of the liquid, upthrust. Okay, so now the reason why this is non-uniform is not because upthrust force change. The reason why this is non-uniform is due to the drag force or the resistive force. So this drag force is D, due to D being proportional to velocity square. Let's say, for example, now mg is bigger than these two, your object will accelerate. So as it accelerates, the velocity will increase. The velocity increase, the drag force increase. Drag force increase, then the acceleration decreases. We will go through that later. So from here, the difference between a uniform velocity graph, I tend to expect a graph that maybe will look like this, right? But for this graph of a terminal velocity of this ball, the terminal velocity of the ball or the velocity against time graph of the ball as discussed in various examples probably look like this, okay? And the reason why you have that decreasing gradient until 0. So from here to here, the drag force increases as the object accelerates. Okay, so eventually at this point, let's say we assume upthrust is so small, it's negligible lah. So at this point onwards, drag force is equal to mg, net force is 0, acceleration is 0. So then we reach this point called terminal velocity. This one also one of their favorites, right? Definitely will ask one. I tell you what, everything here definitely will ask. It's just whether they choose to focus on it or not lah. Okay, so you will expect from this section, of course, including the graphs, okay, including the graphs, this one, I would expect at least about 10 to 15 marks, combination P1 and P2. Combination P1 and P2. So if there's any key things that you feel like you need to rectify, now is the time to go and like be a bit more focused. If let's say you tend to lose marks, let's say you do model papers or you do past year paper by set, right? And then you notice whenever you see kinematics, your brain GG, or whenever you see drag force, you don't know what is happening. We learn that part, no? Okay. So of course, from here, you can see that object accelerates, v increases. Anyway, you can see that velocity has always been part of our discussion. Drag force depends on velocity. Whenever you talk about linear motion, we will describe how something changes, how the velocity changes. Distance travel is important, but not as important as velocity. Okay, so the glue that binds all of this together is velocity. And if you're wondering, when do we see forces again, is when we go to the other side of the change in velocity. Okay, and don't worry, this will be, you know where lah, the places where you will normally find things. After this session, I will pack all the AS review into your OneNote. Okay, so change in velocity, right? Because you see, momentum P is equal to mv. So from here, whenever there's a change in velocity, there's a change in momentum, correct? So what causes a change in velocity? So the first case is where if there is change in momentum, delta P, then you reach your Newton's second law. Force is proportional to rate of change of momentum. Okay, so if they ask you to define Newton's second law, force is proportional, not F equal ma, to rate of change of momentum. My friends, if something that is moving suddenly changes its velocity, but you cannot see what is the force that causes it to change velocity, let's say you drop something, you drop your calculator from your desk, and then the calculator suddenly stop and float in the middle between the desk and the floor. When you're doing past year question at 2 a.m., it's time to go to bed because you just violated not only Newton's second law, but also Newton's first law. Okay, and one, Newton's first law, where we say that the object doesn't change its state, its motion, just doesn't change. Allow, don't know how to spell does not. Its state of motion, unless it's acted on by an external force. Your brain actually know this one. Just like your brain also know kinematics when you play basketball. Right? When you play basketball, do you calculate the projectile before you throw the ball? No lah. Your brain has done the calculation for you. In fact, it has also calculated how much force you should apply. Your brain is a big brain. You just didn't know only. Okay, so it doesn't change its state of motion unless acted on by external force. So in this case, this one is if delta P is 0. There's no change in momentum. This one if delta P is not 0. So there's a process that I don't want to go through again. But then we will reach F is equal to change in momentum over change in time. Whenever you see a calculus thing here, you definitely expect some graph lah, okay? But from this equation, we will apply it to several different cases. The first one that we tend to apply this is collision. Okay, so collision got two type law. The first type is between two balls. You got one ball, and then you collide with another ball. And then, okay, let's take this. Assume this ball doesn't move. Ball A collide with ball B. Bang bang. Then A may move like that. B may move faster, depending on their mass and of course their velocity as well. So when it comes to collision, right? This is the first type of collision. The billiard ball one. This kind of collision is pretty straightforward because it obeys Newton's laws, N1 and N2, and also N3, by the way. I should probably also include N3. So the third Newton's law, which I'm just going to write here, okay? So every force has an equal and opposite reaction force. So I want you to think about how all three Newton's law are currently being exhibited by a simple collision like this. You take ball A and collide with ball B. Okay, so for example, I can say that ball B doesn't change its state of motion until there's an external force exerted on it, because ball B was not moving and then ball B was moving after that, right? So if you look at the perspective of ball B, okay, this is ball B, was chilling here, and then during this collision time, what happened was there's a force of A on B. A go and knock B. That's why what happened to B now is B will now move forward, thanks to this force of A on B. What about ball A? Ball A will continue to move. Okay, label some value. Let's say this is VB. This one will continue. This is UA. Okay. And then reach here is a smaller VA. So ball A would have continued moving at UA, but unfortunately, it collided with ball B. So when it collided with ball B, there's a equal in magnitude and opposite in direction F of ball B on ball A. That's why what happened to A after this was A will slow down because you are moving to the right and then you experience a force to the left, so you slow down. Okay, so these are all examples of conservation of momentum. Every force has an equal and opposite reaction force. So here, there's a past year question where you can then write, if you want to find the force of B on A, because this is the force acting on A, FBA, we will take this one as the change in momentum of A divided by the contact time. How long are the balls touching each other? Because when they collide, right, they will distort a bit. So how long are they touching each other? And then this FAB would be the change in momentum of ball B divided by the contact time. So this T here is your contact time where the balls are touching each other. Okay. So since we know from Newton's third law, these two forces are the same magnitude, so action-reaction pair, FBA and FAB, they are action-reaction pair. So because of this, I can then say that, well, then the force is the same, the time is the same, so the change in momentum is the same. Change in momentum of A is equal to change in momentum of B. So to find the change in momentum of A, I take MAVA minus MAUA, right? Change in momentum of B is MBVB minus MBUB. But this is not the familiar form you have, ma. You tend to, I know UB is 0, but let's just write the general form. So I rearrange on one side, I'll have MAVA minus MBVB is equal to MAUA minus MBUB. So here is where you get your conservation of momentum lah. Okay, the negative here is to show the change. But generally, the way we write it, just to make your life and our life a bit easier, is to consider the fact that we don't know the change in direction. Oh, wait. The change in momentum is equal magnitude but opposite direction. No wonder the equation a bit chat. It's negative. I should draw a graph. No visual, my brain, no cue to include the negative. Okay, so this action-reaction pair, the negative here is to show opposite direction. Okay, forgotten? Or did I purposely forget? Plot twist time. So that you remember whenever you think about momentum, the direction of the velocity matters as much as the direction of the force. This means you get negative and you become positive. Then you become positive and you become positive, and we arrive at our familiar sum of final momentum is sum of initial momentum. Okay. So This is a combination of all three of Newton's law. When two things are moving, and once they will continue moving until they collide with each other. When they collide, they will exert an equal and opposite reaction force to each other. And since we know force is change in momentum over time, the force will have the same magnitude in change, but opposite direction. And finally, we arrive at this equation for conservation of momentum. Okay, so there are many simulations that you can go and view if, let's say, you need more simulation to understand this, but the benefit of saving time, it will not be inside this video today lah. Okay, so if, let's say, popular graphs are like this. Okay, so say I want to draw momentum against time for both balls. Let's take A. A was traveling at UA, and then after that, during collision, it will slow down and then now travel at VA. So this is MAUA. This is MAVA. Okay. We could do a question like this later in example. And then if you think about B, B was not moving. And then once they collide at the same time, B will move. And if you have done, your semester 1 test paper, we have set a question like this. We have shown that the change in momentum of A, meaning this is the change in momentum of A, decrease ma. Delta PA is the same as the change in momentum of B. Okay, this is delta PB. They are the same. Which means if you also are asked to draw the graph of force against time, now extrapolate this line, there will be no force acting on my ball except during collision where the force is like this. And then another force will be like this. They should be a reflection of each other lah, because equal magnitude ma, opposite direction. Close enough. So if we take right as positive, then this one would be FA on B, and this one would be FB on A. So these are graphs that they can ask you to sketch. They can ask you to interpret, especially from this kind of graph. And also, the other thing is F is equal to gradient of the PT graph, because F is equal to dP dt. Okay. All right, so this is the first and a very classic one. There are a few side notes regarding this scenario. The first one, besides the conservation of momentum, is this collision elastic or not? Okay, because we still need to see all the velocities here. So we also need to see whether the collision is elastic or inelastic. Where should I write this? Change in momentum over time. That's collision. Okay. And the collision here, there are two types. Actually, extra collision, besides the one that I show you, other collisions include two-dimension collision. So if you do pass your question, you already know you need to resolve oblique collision. Maybe this ball collide with this ball, and then after collision, one go up and then the other one go down one. This kind of collision, okay? Or collision with wall or floor or ceiling. You know that, you know the drill lah. The wall, floor, ceiling collision, oftentimes the main trap that hopefully you will not fall in again is when we collide with the wall or floor or ceiling and you go reverse direction like that, bang, and then you come back again, your momentum changed direction, okay? The direction has changed already. So if let's say this is 5 meter per second, when you gostan balik, it's negative 3 meter per second. I don't care lah whether this is the wall, the floor, or the ceiling. Doesn't matter. Okay, just know that the total change in velocity is 8, not 2, because you cost to reverse. Okay, that's the thing that people tend to confuse about. And the second way to observe collision is elastic. If it's elastic, there are two equations that you can use, which is the sum of your initial KE is the sum of your final KE. Almost confirm will ask one, either objective or paper 2. It's a very classic physics thing, okay? It's like you go to Chinese restaurant, sure got peanut one, because you don't know when you get to eat dinner. Okay, it's the peanut. Okay, anyway, sum of kinetic energy is the same. KE is conserved. We use the word conserve because it means there is no change. You want to conserve the environment no change. Hopefully. What else? Oh, and also the relative velocity equation. Okay, so I proved it before. I don't think I want to prove it again. So I will just write the equation. The speed of approach, the relative speed of approach, UA minus UB, is equal to negative relative speed of separation, VA minus VB. In my scenario, the same as this one. Okay lah, let B move a bit lah. Okay, maybe not, then my graph will cha-cha. It's the same scenario as this one. Okay, everything is moving to the right. Right here. All object move right. Means what if one ball is moving to the left, or then like ball B in the second question, ball B move to the left. Oh, never mind, ball B move to the left, you give it a negative sign. Okay, then negative become positive. I better draw a box around this. Later you think that hyphen is also a negative. Okay, this one. So for elastic collision, you can use this. Inelastic collision, inelastic simply means KE not conserved. So it means that you lost some energy during collision, maybe as sound or as heat. Because when you collide, there's vibration, right? You try to clap your hand many times and you see, collide your hand repeatedly, your hand will get hot. Okay? You can try lah, but I don't really think it's necessary. Okay, let me highlight the important stuff. Okay, so make sure you at least try some examples, including the 2D collision one, the one with the wall, the ceiling, okay? And also, normally this elastic collision thing is in objective. They will give you some random scenarios of balls and ask you to choose which one is elastic and which one is not elastic. You can use either method, whichever you're comfortable with, but I suggest you keep 2. Because sometimes you can only use one of them. Okay, and of course, conservation of momentum. Conservation of momentum can be applied because Newton's law is a general law. So it can be applied to all collision, everything. Just be aware that for 2D collision, you have to do X and Y. So for this 2D collision, you must do X direction, like your projectile. And then you should do Y direction, if you need to. Sometimes you only need to do one direction, but you still need to resolve. So there is still the resolution of vector here. That's why vector seldom stand alone as its own question. You can ask it all over the place in the syllabus. Okay, so this is your 3 Newton's law exhibited through collision, which is the essence of chapter 4. So now move on to chapter 5. What is chapter 5? In chapter 5, we look more into forces because just this force itself is not good enough, right? So we continue the saga of forces. I'm going to extend downwards here. We'll continue the saga of forces. And then we ask ourselves, if F is equal to change in momentum over time, and momentum is mv, then what I could do is I could have two cases. One case is where my change in momentum is due to the change in mass. So then your force now will look like V change in mass over time. Okay? Sometimes this one can be due to change in velocity. So your force will now be equal to mass change in velocity over change in time. Miss, can change too? Can. Then we use chain rule law. Then it sounds like a mathematics question already. So physics, we stop there. Okay? But change in velocity over time is our good old acceleration. Okay? So this equation, again, confirm will come out one. Confirm use one. If there's anything that you know they will ask in kinematics, is to use this equation. A few note. This F here is net force. Net or resultant. In chapter 1, you have learned how to find resultant vectors. Force is a vector. Second thing, F and A must always be aligned in the same direction. Logic ba? If you pull a box towards you, but the box accelerates away from you, once again, it's not the time, like, are you awake? Maybe you're dreaming. So of course, the force will accelerate in the direction, the object will accelerate in the direction that you apply the force, okay? So from here, you will think about, to find this net force, I also need to know the types of forces. The first thing I need to know is the types of forces. There are more than in this list, but this list is generally good enough for most scenarios. Number one is weight. So when I say types, you must know when the force will appear or when the force is present and which direction and how to find magnitude. When, like, condition of existence. Is it there? And if it's there, do you know its direction? And do you know its magnitude? Okay, so the most steady PP one is weight. You don't know the direction of weight, I also don't know how to help you. Maybe jump from a table and feel where gravity is pulling you vertically downwards. Miss, A2 not the same, I know, but we're now talking about AS, okay? So close to the Earth's surface, everything is just going to pull you down. Because the Earth is flat. Close to the Earth's surface, the Earth is flat. It's a matter of scale, guys. Okay, number two would be normal reaction force. I prefer to call this normal force, and I'll explain why later. And this normal force is always 90-degree to any contact surface. Okay, inclined plane, wall, doesn't matter. So this is a contact force. The force between the two balls, this force, is a contact force. 90-degree. 90-degree. Okay. 3. Tension. Tension only exists when there is a rope. 4. Friction. Normally we use F lah. Okay. This is normally when you have two surfaces in contact. So again, if you study mechanics by now, friction is equal to mu n, or basically these two exist in pairs, unless the surface is smooth lah. If the surface is smooth, then okay lor, no problem. All right, so this tension is normally in spring or strings. Okay, what else do we have? Sometimes we need to consider upthrust. Okay, so This one is whenever there is liquid or water displaced. Fluid displaced. Where the pressure difference is significant. Okay, so this is all the type of forces. They generally won't exist all in the same place. Okay, and friction sometimes can be static friction, like a box on a rough inclined plane. It can be kinetic friction, like the box sliding down the inclined plane. Kinetic friction sometimes include drag force law. Read the question. Okay, so from here we can use F equal to ma. We can find acceleration, and once we can find acceleration, we open up an entire world, because you see this part here, this acceleration can be linked to here. You see this acceleration? So we can draw it back all the way to here. Hence, change in velocity. What causes a change in velocity? Force. What type of force? Depends. Lead the question. Okay. Once we have change in velocity, can we graph the acceleration, the velocity? All can. Can we stuva? Can. Okay. Can. So then this is a classic example. And of course, this is not the only one. This is just a very popular one. Okay. So I think that's a big portion of chapter 5. Just looking at different scenarios and trying to figure out how to F equal ma. But you see, sometimes your net force is 0. Right? So in the off chance where your net force is 0, we use the beautiful word equilibrium. But equilibrium doesn't only need net force to be 0. Equilibrium is a double condition. Your net force is 0, but your net torque is also 0. Correct? Clockwise moment is equal to anti-clockwise moment. Up force is equal to down force. Left force is equal to right force. Also confirm we'll have an equilibrium question 1. And because every scenario is different, and I'll be doing some questions later, so I'm not going to delve too much into this, but I just want you to remember that this one is in any direction, and we prefer, if you think about this in x direction, x and y direction, which will make your brain a bit easier. And then this one is about any point. Prefer you choose a point where you have many forces that you don't know. Okay, one last thing. This normal and friction force, sometimes, I put a note here. Normal and friction, the vector, the resultant of these two vectors, sometimes we like to call this reaction force, much to the confusion of many students. And so when you draw it, you don't want to confuse. You draw normal force, you draw friction force, something like this law. So example of this confusion is the classic old bookshelf question. You have a shelf, and then you put a cable here. Maybe you hang a flower pot here lah. Okay. So if you want to draw the forces on this thing, because you cannot use this equation if you cannot draw the force. You cannot resolve anything in x and y if you cannot draw the force. Draw the forces acting here. We obviously have tension. Tension is acting in this direction. T. Let's say the mg for the beam is here, and the mg of the pot is here. And let's say both center of masses combined means the mg is here. M1 plus M2. This is M2. This is M1. Okay, so I combine these two masses. The center of mass is here. New center of mass. So at the point where the beam touches the wall, there is sometimes they like to call this reaction force. This is R, the reaction force. But actually this reaction force is due to normal. Normal is pointing in this direction. Okay? And friction. Friction is pointing upwards in this direction. So the resultant between these two is R. And R, right? R and T and mg must pass through a common point. Okay? This is so that the net top is 0 about a single point. So it's very common, okay, in objective, in paper 2. So that's why sometimes people get confused between normal and friction and anything about reaction force. Normal force is not a reaction force. I mean, it is part of the reaction force pair, but it is not. Okay, so sometimes they call R and then people get confusion, no? So the same, N and R is not the same. N is equal to R if there's no friction. At least that is generally for physics, not too sure about maths. In fact, I did not study any mechanics in my... Did I study mechanics in maths? I don't remember anymore. Guys, it was a long time ago. I'm an old person. Okay, there we go. All right, what else? What else? Okay, equilibrium. Can be anything from a fishing rod to a bookshelf to a signpost, okay? We don't know. Anything that is not moving is in equilibrium. Not rotating, not accelerating. Okay. Right, we are almost done with chapter 5. There is a slight deviation, not sure why CIE does this, when we move on from this upthrust. Okay, so this upthrust is due to another delta P, but it's not change in momentum, it's change in pressure. Okay, so upthrust, this one, yeah, classic question. What causes upthrust? Because if you, let's say, have a cylinder submerged under some water, then the pressure here, P1, and the pressure at the bottom surface, P2, so this is area A, is not the same. P2 is obviously greater than P1. Because why? Water pressure is H rho G. There is past year question that asks you to prove why water pressure is H rho G. I think it's also available in your notes, so you refer to that one, okay? Not that important. This one here, we generally leave it at the side because they seldom ask, but this pressure difference is the cause of upthrust, because your upthrust is equal to P2 minus P1 over A. And then from here, we derive this one as rho Vg. You want to know derivation? Can. Will they ask you? Sometimes they like to combine this with forces one, because it's also a type of force, Like there's an equilibrium question, past year question, where they put this cylinder inside a water and then hang the cylinder. Then I put my flower pot long time never water already. I just submerged the entire flower pot in. This will cause my center of mass to shift to the left, because now this flower pot is lighter. Okay, then I can have upthrust. That's how they can just add it in. For MCQ, they can focus solely on upthrust, solely on pressure, but also don't forget about atmospheric pressure. So the U tube question, the W tube question, there's only one question now, okay? So here at most is about 3 to 5 mark. You don't want to do is also okay. You can just like, you know what, never mind. 2 to 3 marks. Sometimes no, don't ask at all. Let me miss out anything here? Of course, density goes without saying that you should be able to do mass over volume. That one, I also don't know where to write. Find density. Okay, what else? This part here, equilibrium and types of forces, I will expect another, I guess, 5 to 10 marks here. I'm just ballparking, okay, if I set questions, okay. Combination of P1 and P2. When it comes to collision, all types are 2D, wall, floor, container, whatever, change in momentum one. This one here is another 5 to 10 marks. Combination of paper 1 and paper 2. including your Newton's law lah. So can go up to 12, I guess. 5, 10, 12. So if these are important things where if you don't know, then it will really affect your final marks. And okay. All right. Finally, chapter 6. Means chapter 6 is related to velocity, man. Don't forget. What is our main chain? Our main chain is a change in velocity. So velocity, whenever there's a change in velocity, there is momentum. There's a change in momentum. We can say the object is accelerating. But we can also say, because there's a change in velocity, that there is a change in kinetic energy. And because there's a change in kinetic energy, there is work done. So a useful way when I was a student to think about work done is whenever there is work done, somebody is changing energy from one format to another format. And if I can identify what that change is, what that transfer is, I can do the question. So it's not so much as like memorizing, it's more of like, let's say you have a ball falling. Okay lah, it's a very boring one, ball falling. So of course the kinetic energy increases. There's work done by gravitational field. Somebody is doing the work to convert KE, to convert GPE to KE. Okay? So this change in kinetic energy shows me that there is work done. Work done by resultant force. So change in KE here shows me that there is work done. And oftentimes this work done is by some form of resultant force. Of course, you need to study the scenario lah. You can break it down so that it's not just the resultant force, but in a nutshell, here is how they are interlinked. This part here can be tied to F is change in momentum over change in time. Okay, work done. So as mentioned just now, the important idea about work done or energy, by the way, W is equal to Fs, and I hope you know the definition, product of force and displacement in the direction of the force. Okay, so work done is this one. So when we do work, we are changing energy. Can I write here for you? Change the energy from one form to another, or one type to another. I guess the next question would be to list down the types of energy, right? So the types of energy that we have in your syllabus at this point in time include, number one, work done against friction. I know, very potong steam. Hey, friction is a thing, what? W is equal to Fs. This S is the displacement traveled by the object, the actual distance traveled by the object. Okay. Number two, there's obviously our good old kinetic energy. Oftentimes I use KE, but I look at past year questions, I like to use EK. Okay lah, I also change. I'm flexible, half mv squared. Means they can ask proof. They got asked before lah. It's about 3 marks lah, the proof. Generally, whenever there's a proof, it's about 3 marks. You decide lor. Then they will only ask one proof per paper too. So it's not like they're going to ask you to prove for every single chapter, for every single question. So the 3 marks is important to you, go learn the proof. I find the proof is pretty okay. Gravitational potential energy. EP is equal to mgh. I like to put a delta here because I am the kind of student that will forgot to minus the change in height one. I will always take the final height. So I put delta there to remind myself to minus the height. Okay? Just like oftentimes when I write this equation, I will always use net force or I write a sigma in front just to remind myself, hello, please think of all the other forces. Okay, what else do we have? Elastic potential energy. So for elastic PE, I also don't know because we also use the same, we use the same. I use EPE lah, and this one I use GPE, but for your syllabus, they tend to use something else. So we can find half fx or half kx square. Just a brief reminder that here ties into chapter 9, your Young modulus, because this is also known as strain energy. Okay, so these are your types of energy. Strain energy. And if there's strain energy, there's force, there's Young modulus, you can stretch stuff. This chapter can also be linked to Young modulus. Okay, anyway. Area under graph. So energy is always area under the Fs graph. For spring, the distance traveled by the spring, so-called, is actually this area. So this is your EP. Of course, this one is your X, okay, which is W. So whenever we convert between these four, of course, there are more energy. Oh, wait, there's a fifth one. But you know lah, fifth one, we did it before. This is the electric PE. That one will be Q delta V. And normally, if got electric PE, there's no GPE one, because the object very light normally. So I think if you came or you watched the review for chapter 17, electric fields, I'll talk about this. So I'm not going to really focus on this. So whenever there is energy, like all engineers who study energy, we will then move on to think about work done. Not work done, sorry, power. Power and efficiency. So power is work done over time. Sometimes I like to see the change in energy over time. Sometimes we can use FV. But the condition to use FV is what? What's the condition to use FV? Where did FV come from first? Do you need to know the proof? Yeah, same lah. My same comment. You need to know. If you don't know, it's not the end of the world. This is Fs. Actually, the actual definition for power is rate of work done. See, rate all over the place. Calculus is very useful. dW dt. So power is equal to d dt. W is Fs. Right? So I'll put the F here, I'll put the S here. So P is equal to FV. So from the derivation, you should be able to tell the condition. First condition, this one is constant. Constant net force. Okay, and second one, your V also must be constant. If not, then what number are you going to put? Average. Okay, so depending on the scenario, I can use this equation. But this is the more OG equation, the more OP one. This one. And efficiency, I hope everyone here knows. Okay, we will take either input power, the ratio of output to input power or energy times 100%. The output one is useful. Read the scenario, figure out what is useful to you. The input one is not useless, the one that you put in. Okay, that's it. That is it for, okay, this one is another 5 to 10 marks. Here. So, this means 10, 20, 30, 45. I think we are looking at about 55 mark out of 130 for today's thing. And I think we have spent quite a number of time. We started with change in velocity, and here we branch off into 3 directions. But hopefully, as I link them, you can see how they are interconnected. And they are connected by this main mother, change in velocity. You change your velocity, everything changes. COVID-19 tracing. This is the first case. Okay. So if any branch you don't know, because here, this one is about 10 to 15 marks. This branch is about 20 to 25 marks, can go up to 30 depending on the flavor. Again, combination of P1 and P2 lah, okay? This one can go up to 20 also. One. This one is also another 10 to 15 marks. So if you take the end range, it's about 55 marks total out of 130. So that's one third. One third of your, yeah, more than one third of your syllabus, which it should be lah, because mechanics is an important study. It's a study of how things move, how to make engine, how to make your sports car, how to code if let's say you want to build a game so that the mechanics of the game doesn't feel weird. All right. So we're going to jump on and do some examples. There's a question in the chat. For GPE, change of GPE is mg. I mean, I use change in height lah because when I'm talking about this, right, it's all change one. Sorry, maybe I wasn't very explicit. So this one can be half mu square. Okay, so because whenever they give you a scenario, okay lah, there are some really easy question where they put a ball 2 meters above the ground and then they ask you to find the GPE lah. But this one has no meaning to me. What has meaning to me is when the ball fall to the ground, what is the change in energy? Okay. Oh, I missed out one. It's a 1 mark question. Work done by guess. I don't know why it's here, by the way. And yes, for this one, you can only use if they're both constant, okay? Can? Actually, it's not really net force, it's just a constant force. You need to look at the scenario lah. We'll do some questions lah. Okay. If your velocity is not constant, what velocity do you use? I mean, unless it's an instantaneous power at this point in time. Okay. So this equation always a bit sketch one. Try to default to the top one. The P is FV equation. Actually, if you've done model paper 2, MP22, the one with the inclined plane, the truck up the inclined plane one, that's a very good example. Okay. For the elastic potential energy, we use half Fx because force is not constant. So we find area under the graph. If the force is constant, like for example, friction is constant, we just multiply by distance straight away. Because if force is constant, your graph is like this one. Force is constant, I don't know. So then area under the graph is this one. This is W. Okay. So this extension, if let's say you want to find change in elastic potential energy, the extension, I assume you extend from 0 lah. But if you don't extend from 0, then you take your initial state minus your final state. Let's say you start your extension here, and then you end your extension here, then you find this area. If they stretch from 0, then the change will start from 0. There will be the green color shaded area. Read the question. Okay, there's always a change. If you don't change the spring, how do you store elastic potential energy in the spring? The spring is just no force. Okay. So you look for area under the graph, depending on where. It's like integration, guys. You are either integrating from x equals 0 to this or x equal to here to here. Okay or not? Chat. You let me know. I'm gonna just, as a footnote right here, work done by Cass. W is P delta V, volume. So, I mean, if you did A2 already, you will know what is going on now, but you don't yet, or you forget your A2 because you were studying for your AS. This one is the piston question. You got some gas inside. Then if let's say we compress the gas, I'm not gonna, I mean, this one, it came out in paper 2 before, but very level 1 stuff lah. No big deal. So we're going to move here. Here to here is your delta V. So W is P delta V. Okay. This entire region, green color space that I'm shading is being compressed. So one footnote about work done and on the work done by and on the gas. If W is positive, put here. Positive means volume decrease. You add energy to the system. You press in, you add energy to the system. Work done on gas. If W is negative, this means volume increase. The gas push out. If the gas do the work, gas loses energy. That's why negative. Work done by gas. That's it. Sometimes they like to say work got out lah. But my English teacher is scolding me. You go out, go where? I don't know. Work got out. All right. So give people a few moments to ask me stuff if they want to. But in the meantime, I'm going to curate and crop some questions to discuss. And then I will come back here and maybe provide some suggested examples to do for each section. I'm going to do all the ON20 one. Okay, there's a question in the chat saying that negative W means lost. I mean, in this case, the negative W, because it's very hard to think about the force. Yeah, don't think about force here. Lah. You can, but it's a bit unnecessary. For gas, it's easier to consider whether the gas is increasing in volume or decreasing in volume. Okay, so if you want to think about F and S as being the same or opposite direction, then it may seem like force and displacement is always in the same direction. Because right now, because now you're thinking from the perspective of external force. So if let's say there's an external force pressing in, then this is the direction of S. So the external force is doing the work to increase the energy of the gas. But then now, when you pull the piston out, your external force is like this. Your displacement also same direction, what? Because you're pulling the piston out. Then the external force is increasing the volume. Okay? Whether it's external force or it's the gas, the direction of force is still the same. So it's going to be, let's say it's the gas, force of the gas. So this one, if let's say you think about external force pushing the piston in, so this is work done by external force on the gas. Hence, on the gas. Okay? And then let's say the second scenario. I draw the piston again now. Let's say we talk about the second scenario where we go from here. This one is a little bit more confusing now. Prefer to look at volume, but maybe there's no one way to look at things. So let's say now the gas wants to push back out. So this is force from the gas, collision of the tiny, tiny gas particle. And this is the direction of S. So this is work done by the gas on the external environment. So it's atmosphere. So work done by the gas. Actually, this one I should change color. It's green. Actually, no. This one cannot be green. Cannot blue lah. So work done by the gas for this one. By the gas. So when there's this change in volume from here to here, it's work done by the gas. Does that make sense, my friend? If you think about forces, then you need to bring in the third party. That is where sometimes people can be a bit confused lah. Because here is work done by external force, which by the way is your atmosphere on the gas. Okay, so this is on the gas. On the gas. Okay, Mo. Nothing about direction of force? Can. It's just that it's not always the same force acting on it lah. So there's two perspectives. Okay, keep asking. I'm going big questions. The chat. I mean. Oh, by the way, slide bar. Forgotten. Talk about torque. Torque is a force that causes turning effect. You will find torque using the equation force times perpendicular distance. So this D, F is perpendicular to D. If they're not perpendicular, you resolve somebody, preferably F lah, but you can also resolve your perpendicular. You can resolve your distance to take the perpendicular one. Okay. But oftentimes people will resolve. Okay, so net torque is 0, you will get equilibrium. But sometimes net torque is not 0, okay? Then the thing will rotate lah. There is rotation. In fact, it will rotate faster and faster or slower and slower. But that part is not really in your syllabus. Just know that if there's net torque is 0, you should know how to calculate the net torque. That's all. MCQ1, this part. Yeah. So entire section today will be 50. Paper 1, paper 2 will be 50 to 60 marks-ish. This equation only works if pressure is constant. If pressure is not constant, then cannot work now. This one is only for constant P. Pressure is not constant, you can't use the equation. If pressure is not constant, then it will be area under the PV graph. Let's say the pressure, okay, never mind. That one a bit too much. Let's say the pressure changes like this. Okay. You pull out the piston, less pressure, this one quite logic, right? So then this is your work done. Not in your syllabus, but the work done is nRT ln V1 over V2. Let's say you compress the gas. Compress. Not in AS syllabus, not in A2 syllabus. I guess if I'm free, I can derive the equation now, but it's not important. Area under the graph. The most they can ask you is ask you to either shade the area or they give you an MCQ with a bunch of graphs and a bunch of shaded area. You decide which one is the area to show work done. Because actually work done, you see work done is F integration of F ds. Okay, this is what I mean by if you don't calculus in physics, sometimes very hard, you know. Force is pressure times area ds. Area, assuming that it's a piston where the area is fairly uniform, so I can change this to pressure. This one is dV. Integration P dV, which is area under the PV graph. Okay or not? So actually work done is an integration, but which is why we find area under the graph. But it's not explicit in your syllabus or in AS physics syllabus because we are trying to make it as user-friendly as possible by not including calculus. Okay, so if you just, for purposes of answering your AS, your memory work law, work done is P change in volume, can only use for constant P, and positive and negative depending on the change in volume. All right. Okay, another question. Net torque and net force must be 0 in all direction. We don't say net torque is 0 in all direction, because torque only got 2 direction, clockwise and counterclockwise for now lah. Unless you talk about a 3D plane, then that one is not in your syllabus anymore. It's very far away. The one need vector calculus. I shall not talk about that. Okay, so we prefer to say torque is the same about any point. Yeah. Any point. This one is any direction, but x and y is easier for you to see lah. Your x and y axis is relative one, you know. Okay, which value should we use pressure? Okay, I told you already, it's the constant pressure. There should be only one value of pressure when you use this equation. Okay, so just use, no, this pressure is the pressure inside the gas. Pressure of the gas. Okay. Does that satisfy also constant P? P is pressure of gas. I don't care what the atmosphere pressure is. It's not part of my system. My system is just the gas. And all I care about is the gas. Okay. That's why I don't recommend using the direction of external forces, because you are bringing in the second party in, and then you may get confused because I only care about the system. And the system is the gas. See, I highlight gas, gas. All right. Just like when the ball is falling down, it is acted on by gravity, but we don't really care about the work done on gravity by the ball, right? Don't care. No one cares about gravity. I mean, not no one cares, but it's there, and it's not part of our system. Our system is the ball falling through space. So being able to identify the system that we are analyzing will help your brain, because we can't study everything. It's too much. The brain cannot too much. So you must analyze the system. For example, if we go to okay, we will do some questions. Then maybe I'll provide some suggested ones for you to go and try. Then you call it a day. So it's ON20 paper 21. For example, right, you see, if I look at this, my entire system is the fishing rod lah. It's very obvious one what the system is. It cannot be the water, right? Why do I care about the water? It cannot be the fish, right? I don't care about the fish. Does the fish have forces? Yes. The fish obviously have force, have upthrust, there's tension, cause the string. I'm thinking the string is tied to the fish. I don't know. Okay. My system is also not ground. Is there contact force? Is the rod pressing down on the ground? Pretty sure it is, but don't care because my system is the rod. Okay. Always identify the system that you're trying to analyze, and then the rest just push one side. Don't care. One out. All right. Define moment of force about the point. So this one is the product. Oh, suddenly need to change pen thickness. Product of force and perpendicular distance from that point. Determine the SI base unit for moment of force. So moment of force, they don't call it, moment of force is also known as torque, okay? I prefer to call it torque so I can use tau. Never mind, I'll use it here also. Force times distance. If they want SI base unit, yeah, this one is mad. Basically, you just keep breaking apart the equation to the simple form, then you can substitute the unit. So hence, unit of tau will be kg, ms -2, distance is m, so kg m square s -2. Okay, done. Do you need to show working? Yes. Normally the marks is like that one. I show the working, at least this line, at the very least this line, and then the final answer is 1 mark. You don't show working, I don't know how you got the answer. You may get 0. Okay, so here is a regular old rod. Okay, you are given the weight of the rod, the length of the rod, the density of the rod. Calculate the cross-sectional area. Oh, 3 marks. See, physics can get 0, meh? Cannot lah. Density is mass over volume. Okay, but volume is area times length. So I rearrange first because I don't want to move things around later. Rho L. Okay. Then I continue lor. This one will be, it has a weight of 5.2. So the mass need to convert, right? 5.2 divide by 9.81. Big divide. 790. Length is 2.4. Of course, your area is going to be small because this is in meters square, to which we need to convert later. So let me press my calculator. 2.795. I guess I'll put 2.80. Okay, times 10 to the power of -4 meter square. So if you want to convert meter to mm, think about millimeter. Millimeter is 10 to the power of -3. But you don't want to change the value, right? Because you can't change this 2.8 times 10 to the power of -4. So 10 to the power of 3 times 10 to the power of -3. That way you have the milli here. Okay? And don't forget to square. Did I change the value? No. Write this if you always got problem deciding whether you should multiply or divide the prefix. Okay? So here we'll make this into mm square. This whole thing. And then what is this part here? This part here, 这边乘 will become A is equal to 2.80 times 10 to the power of -4 times 10 to the power of 6. So this is 2.80 times 10 to the power of 2. Can you leave your answer like that? Of course you can. No problem. Can you write 280? Also can. Not a problem. Okay, so let's see where the marks are. If we see density as this one, and then eventual conversion by G, you get 1 mark, C1. You substitute everything else in correctly to arrive at this one is C1. You convert correctly to this one is A1. Look, certain people can convert directly without going through this step 1. I'm just going through the step for people who need it. It's okay to take extra step. No problem. C. Okay, this is fishing rod AB made from the rod in B. So this is my rod, my little fishing rod here. Okay, so this is my system. The end A is resting on the ground, the string is attached to the other end B. A support stick exerts a force perpendicular, good thing perpendicular to the rod at point C. The weight of the rod acts at point D. Tension T in the string is the direction perpendicular to the rod. The rod is in equilibrium and inclined at 56 degrees to the vertical. The forces and distance along the rod of point A, B, C, D are shown. Okay. Show that the component of weight that is perpendicular to the rod is 4.3 Newton. Okay, so we gotta resolve. So generally, right, the way they try to help you is they will try to ask you to resolve some force first to hint at you about which direction you should consider. So if they ask you to resolve the weight, meaning now we are going to consider forces that are parallel and perpendicular to the rod. So I'm going to split this one into perpendicular like this and parallel this way. Okay, so this component here don't have angle. This will be 5.2 sine 56 because you're opposite the angle. So 5.2 sine 56. 4.3 Newton. Okay, wait. I need to answer some question from the chat first. Let me see. 5.2 sine 56. 4.31. Okay lah, I write 4.3109. 4.311. Can, which is more or less 4.3 Newton. So the question is always like, Miss, should I take 4.3 after this or should I not take 4.3 after this? Look at mark scheme. Okay, you see here? Did they take 4.3? So if you want to look like mark scheme, you should also take 4.3. But Miss, if I take 4.31, then my answer here slightly different. Can? Can. No problem, as long as you show your substitution and you're working clearly. Okay? And I will guarantee you that somebody here will have that sense of doubt again when they do some other random question or random paper. And if that happens, look at mark scheme to reassure yourself. Just take 2 lah. And then I know this is not a general practice in maths, because maths, I don't know, you take many SF. I don't know why, but okay, sure, more accurate. But for physics, we only take 2. Okay, you see all their numbers are given to 2 SF, 4.6 Newton 2 SF, 5.2 Newton 2 SF. You write 4.3 Newton 2 SF, it's perfectly acceptable. Okay, you want to increase 1 SF also can, no problem. Just show you're working carefully. This question is very nice. They even tell you which moment to take. Okay, but let's say they never tell you take moment about NA. How do you know you're going to choose A? Why can't we choose B? Well, if you want to find tension T and you choose B, tension T passes through point B. So there's no torque due to T. T doesn't exist in your equation. That is not a good choice. So you should take A because number 1, there is normal force here that I don't know what this is. And there's probably some friction. I'm guessing if the rod would slide, it will slide to the right. So there's probably some friction here. You don't know the friction, you don't know the normal, so might as well you take this point as your reference point. So if this is your reference point, then we can do sum of clockwise is equal to sum of anti-clockwise. So who is clockwise? 4.6 is the stick is, let's say you push on the stick, is what causes the rod to fall in the clockwise direction. So we will take 4.6 multiplied by this distance, which is 1.8 meter. Okay. Anti-clockwise is the force that pulls the rod down so that it's parallel to the ground. So that would be T times the entire length, because T is at the furthest end. That would be 2.4 plus 5.2. Oh, sorry, 5.2 sine. Miss, can I just put 5.2 sine 56? Can, no problem. Whoever you want to put. You can put, look, this one you can put 4.31. You can put 4.3. You can even put 5.2 sine 56 because you know you want absolute accuracy. Can, just put, no problem. Examiner can see one. But, you know, I just want to give the examiner an easy time because the examiner is going to mark many papers, you know. So anyway, what is the distance for this? 1.2. Okay, so then I press my calculator. I'll find my T as 1.3 Newton. I guess if you put 4.31, you may get a slightly different answer. If you take 5.2 sine 56, you will get a slightly different answer. As long as you round to 2SF, the answer is the same. It's okay. Round to 2SF, make sure the answer is the same. Can? I myself, I think if you notice, have a habit of writing in 3SF lah, because I did a non-A-level syllabus where the standard was to write it in 3SF. Final answer, you write 2 to 3SF, you are generally solid, unless it's absolute uncertainty or the estimating questions lah, okay? Alright, I'm gonna write some 1.3. Okay, next. A small block, wait, let me check the questions. How to get F? Ayo. Okay, extension time. How to get F? Let me think. I'm trying to think of an easy way. I guess we don't have an easy way. Okay, I tell you what to do, Junlo, you go back and do, okay? But how to find F? Good question. Okay, where's my question paper? Hilang ba? In order to find F, you will have to use net force is 0. Okay, so if you want to use net force is 0, I will resolve my forces differently. Of course, you can stick to this direction, but then it's going to be a pain, okay? So just resolve lah. So this one will resolve one component like this. Change thickness. I'm going to resolve one component like this, and then one component like this. We see if this is 56, then this is 34. My math's correct? Yeah, 34. So if I resolve T like this is 56, right? So this is 34. So I have 1 point, plus T is 1.3, I'm sticking to 1.3 now, okay? So this is T is 1.3 cos 34, and this is 1.3 sine 34. Okay, one done. Next. This one. This one, the force is actually acting in this direction. Right? I transfer the direction of the force. Push up. Okay, so if I resolve again, one is in the y direction, one is in the x direction. Again, I need to think about the angle. So this one is 56. How do I transfer the angle? This is 34. Like that. So this is 34. So this will be 4.6 cos 34 and 4.6 sine 34. This one no need to resolve. Okay. You have normal force here. Let's say you have friction here. These two also no need to resolve. So you do sum of the upward force law. Sum of upward force is sum of downward force. What's the upward force? 4.6 cos 34 plus n. For downward force, not. Got 1.3 cos 34 plus 5.2. So up plus up is equal to the downward force. Okay, then I can find n. So this is how I find the other two forces lah, if I want to find them. Okay, repeat again. For left force is equal to right force. So what's the forces pointing on the left? We have 1.3 sine 34 plus friction is equal to 4.6 sine 34. Okay or not? That's how they can ask you to find the friction. But there are many steps. Good news! If there's many steps, means there's many marks. Then this will be an entire question on its own already. They won't ask you to find the unit, SI unit, or the area. They will just give you all the values. That means they are solely testing on whether you know how to do equilibrium, hardcore equilibrium, rather than a combination of unit and other stuff. Normally, they will combine for paper 2 so that they can cover more of the syllabus and so that people don't totally GG, you know. It's like total disaster. Okay. So this block is lifted vertically upwards by a toy aircraft as illustrated in figure 2.1. As the block is moving upwards, the string breaks at time t equal to 0. block initially continues moving upwards and then falls and hit the ground. Do you know why it continues moving upwards or not? You imagine, this drone is carrying the block. So the block has a velocity of 1.96. So initially, the block was traveling upward at 1.96 meter per second. In order to maintain the 1.96 meter per second, you need to overcome the weight of the block. But unfortunately, the string is no longer there. So the weight of the block mg will pull the block down. But the block cannot suddenly go down. It needs to stop, slow down to 0, and then only increase velocity. So this block is going to rise up to the highest position, and then fall down. This is the trajectory of the ball. Okay. All right. Okay, graph given. State the feature of the graph to show that the block has constant acceleration. Well. Yes, constant acceleration because the gradient is constant. So I'll say that the gradient of figure 2.2 is constant. Or I guess you can say figure 2.2 is a straight line. That is also okay. No problem. But constant gradient is more legit. All right, next. Determine the height of the block above the ground when the string breaks at t equal to 0. Ooh, interesting. Okay, since I draw this, I draw this one already. Might as well use this. Okay, so what we need feels like a kinematic question. So when it crashes to the ground, let's say this is the ground. Here is where the string breaks, right? String break. So I actually need this distance. S. Is this the displacement? Yes. Can you find the displacement? Can. Because this area is positive ma. V positive means it's moving up. So this part is actually here until 0. Okay? And then after that, when it's going on the way down, here all the way down to the floor is this entire area. Okay? This whole thing. You minus the area of the triangle. Can you stuva? Can, but they give you graph already. No need to stuva. Okay, so what first things first, in case I mess up, is I'll find the displacement separately. Do you need to? Nope. But I know I am a student who make many careless mistakes because I have done quite a few papers and I understand my weaknesses. So I will always try my best to get marks even if I got weakness. So this one is moving up. So upward displacement is half 1.96 times 0.20. This is 0.196 meter. Means here I can round to 2SF. I suggest you don't round first lah. You see this one, they write 3SF, 1.96, you keep 3SF, okay? Downward S will be half, what is the 6.96 and 0.7, okay? 6.96, 0.70. So this will be 2.401 meter. So hence, the height S will be equal to 2.401 minus 0.196. Here, you want to round, you can round. You don't want to round, also can. 196, this will give me 2.205. The mark scheme answer is 2.2. You want to stick to 1, up to you lah. It's up to you. You can put 2.205, they're all okay. More SF is okay as long as it doesn't look like a telephone number, okay? All right, so there's another method, obviously. You can use your STUVA. Let's write down, we're looking for S. We have the time. Time is 0.90. Or time taken for it to fall to ground is 0.90. Initial speed is 1.96. We even have final speed, negative 6.86. We even have acceleration, I presume is negative 9.81. But since they never give me, and I can find, because, 1.96 divided by 0.20, is it 9.81? Oh, it's 9.8. So let's assume that, and it's negative, by the way. Let's assume that you don't want to find the acceleration. So you can use S is half U plus V times T. So half U is 1.96 plus negative 6.86 multiplied by 0.9. This one also can. Of course, your working will be less to right lah. 1.96 minus 6.86 times 0.90 divided by 2. So I get the exact same answer, 2.205. Miss, why this one got negative? Because the final position is below initial position. You start from here, you end here. So when we measure displacement, we measure from starting to ending, right? So it goes from top to bottom here. So it's negative one. That's why you get a negative. We expect to get a negative, okay? And in fact, you should actually take and for this one, I just took the big number divided by small number lah, because they just want the magnitude ma. But by right, this thing should be negative, and I should add these two together, strictly speaking. Okay, anyway, let's continue. The block has a weight of 0.86 Newton. Calculate the GPE of the block between t equals 0. The difference in GPE, mind you, between t equal to 0 and t is equal to 0.90. Need to find initial and final minus. No need lah. Your block is traveling like this, ma, correct? So here is t equal to 0. This is the initial. This is the final. I just need delta H, guys. And delta H is here. So I can just take the change in GPE will be equal to mg change in height from t equal to 0 to t equal to 0.9, which coincidentally is our 2.21. Can I put 2.2? Can. Can I put 2.205? Can. You like lah? Okay. We got the weight 0.86. Okay. The thing is, your examiner's mark scheme will be 2.2. So unless and then this is 1.9 joule. Okay. If not, there is 1.9006, 1.899 is the same. Okay. Doesn't matter. Okay. I'm going to stick to 2SF to normalize the 2SF in the physics paper. Okay, so sketch a line to show the variation of distance moved by the block with time t. Oh, for the first 0.20 seconds. Well, the block is slowing down because it is still on the way up, right? 0.20 second is here. The block is slowing down. So you should draw a graph of decreasing gradient. Okay, and then the gradient should be 0 here. That is the 2 marks. Okay, because at 0.20 is where it reaches the maximum position. Here's the mark scheme. Curved line from the origin. Okay, and then the gradient of the curved line decreases, so that is 0. Because why? The velocity here decreases until it is 0 at 0.20. So the gradient should be 9.8 here, decreases 1.96 here, and then decreases to 0. Okay, next. A block of greater mass is now released from same height with the same upward velocity. Air resistance is still negligible, so there's no air resistance. State and explain the effect, if any, on the increase of mass with which the block, the speed with which the block hits the ground. Or basically, they're asking you, if I increase the mass, will the speed when the block hit the ground change? Everything else is the same. So the first block, let's say this is M, okay? Travel upwards, then it crash to the ground. Second block, same dimension, I presume, or there's no air resistance, so it doesn't matter, but let's put it at the same dimension. Same initial speed, still V, this 1.96, okay? Will it fall at a higher speed? Lower speed? Same speed? And explain. Well, there are a few clues here to tell you the answer. Number one, in your calculation, did we ever use mass to find the final speed? No. I mean, this gradient is gravity, and gravity is the same, it's independent of mass. But miss, we use mass here leh. You don't forget. We can take the change in potential energy is equal to the change in kinetic energy. So mg change in height is half mv square minus half mu square. Let's say the initial speed, you account for it. All the mass can go away. So the change in energy for a gravitational potential energy to a kinetic energy the mass will not change anything. Okay, if it's a pure GPE to KE conversion because of gravity. Gravity on you and gravity on me is all the same. If we all jump out of a window, you and I will all accelerate at 9.81 meter per second square. Okay, so the answer will be like no change. Wow, cannot see. No change. Need to explain though. State, explain. Okay, why is there no change? Because the acceleration of free fall, which is gravity, is not dependent on the falling mass. Hence, no change. Hence, no effect. I prefer to state the answer first, but you like lah. If got air resistance, then got change. Okay? Go do some past year question. The one with air resistance ones are... Okay, hang on, let me go and dig a bit. So, what if there's air resistance? Then, you would involve the... Let's see. Dun, dun, dun. I mean, I want to suggest the raindrop question. It's also not obvious that... I guess the raindrop one also got a bit. But anyway. ON20 paper 22 question 1B. Go do. If let's say I change the dimension or the drag force, what happens? This one no change, so don't care. Question 3. Define force. F equal ma will get you 0 marks, okay? Can. Many times now lah. Now I paste the mark scheme here lah. Rate of change of momentum. All definition for kinematics, mechanics are all rate of change of something. Okay. Don't write the equation, no mark one. Okay, a ball falls vertically. Okay, so this is our classic collision question. It's going to rebound, collide with the floor, collide with the wall, collide with the ceiling. Which is what sometimes I feel like doing when you are in quarantine for too long and cannot go out. Okay, so the ball reaches the floor at 3.8 meter per second in contact. Oh, there's a contact time. Before leaving at the speed of 1.7. So the ball is going to touch the ground and then it's going to compress and then leave the ground. Hopefully you have watched the slow motion video. Time for a break from me talking for 1 minute. I will show you the slow motion video again in case you never seen before. So anytime you just want to stare at it to meditate, you can just go and find some slow motion videos. Alright, so here's one. Okay, so you notice when the ball touches, it will compress, and also when it leaves, it is actually oscillating a bit. That's why it lost the KE, because the KE converted to the oscillation of the ball as the ball, leaves the floor. Okay, easy question first. Calculate the loss in KE. Well, you see, in physics, we concern ourselves with change more than the absolute value. Anyway, I'll take half mu square minus half mv square because I just want the loss. So half, what's the mass of our ball? 0.062. U square is 3.8 square minus 1.7 square. For the nth time, and I will say this for the people who need to hear this, so bear with me. This is not the same as this. I hope you don't need me to explain why. All right, so this one will be 0.36. Just, you know why, okay? Just press your calculator, they're not the same. Okay, so where are the marks here? Apparently, if you write the equation, you will get a mark already. Very nice. If I see some half mv square, you get 1 mark liao. And then correct substitution leading to this answer is A1. You don't show substitution, you will lose the second mark. Determine the magnitude of the change in momentum. Very nice. Change in momentum. See, change. Okay, they want magnitude only, right? I can take mu minus mv. Okay, they just want magnitude. I take the big one minus the small one because I don't like negative numbers. But I know that there could be a negative number. I'll figure it out later lah if I need to. But that's how my brain works. Okay, so is this correct? I just now mentioned already, right? Positive. I mean, I'm going to take up as positive lah, down as negative, just to help the brain. Okay, so it's negative 3.8 minus positive 1.7. See? Negative 3.8 minus positive 1.7. So if you were thinking that that was correct, no. Miss, why this one no need? You square negative 3.8 is the same as 3.8 ma. You square 1.7 is the same as 1.7. It's the same. When you square, the sign doesn't matter. That's why energy is a scalar. Okay, the sign in this perspective has no meaning one. So in this case, I actually should take 0.062 3.8 plus 1.7. Okay, so it's up to you lah whether you want negative 3.8 minus 1.7 because I took the initial minus the final. I mean the initial minus the final. Oh, you can take final minus initial. Okay, we just want the magnitude. So finally, what I will get is negative 0.34. Let's say you write like this, don't worry. Just continue 0.34. Or you cross everything out and then you rewrite everything again. Take MV minus MU. Okay, the magnitude. Wow, so nice. They are very nice today. Average force. F is change in momentum over change in time. 0.34 divided by, what's the time again? 0.8, 0.081. 081. Very nice. 4.2 Newton. Okay. Everything 2SF is fine. Use all this information to calculate the magnitude of the average force of the floor on the ball during collision. Floor on ball. Ball on floor. It smells like action-reaction pair. Is it all 4.2? No. Why? Well, because you look at this ball, the change in momentum of the ball was 0.34, correct? Actually, it's positive 0.34 lah, because the ball turned to the positive direction, moving up. Okay? But this one is for net force. Every time this one is net force. That means there's another force here. What's the other force? What's the other force? Well, let's consider when the ball is colliding with the floor. Ball is here. It's squished a bit. This is my squishy ball that looks a bit like Pac-Man, but you get the idea. It's squished. So when it's being squished, right, the average force here is 4.2. Is it 4.2? No. This is the force of the floor on the ball. Can? But also at the same time, there's weight, our good old mg. And the 0.42 is your net force. So you need to include mg. Yep. Miss, this one come out before. Yes, correct. It came out before. In fact, I will now go and find that question so that this does not happen to you again. This situation, go try. May, June 18, paper 2-3, question 3. It is almost the same. Almost. Not identical, because that would be irresponsible, but almost the same. If you understand that, this one should be fine. And I can't. I'm gonna move this over to downstairs and continue the story. Right, so here's our story. This change in momentum of the ball is the one that gives rise to our net force. Because this is the momentum, the change in momentum experienced by the ball. So this one is the net force experienced by the ball. The force on the ball during the collision by the floor on ball, is this one. So what I actually need to do is net force is equal to F floor on ball minus mg. So the force of the floor is equal to net force, which is 4.2, plus mg. Do we have mg, guys? We have the mass, right? It's the mass 0.062. So 0.062 times 9.81. 9.81 plus 4.2. It looks like 4.81, or I guess 4.8 is enough. Okay, and because of Newton's third law, these two numbers should be the same. Newton's third law. Because the floor will also experience an equal in magnitude but opposite in direction reaction force. So this is force of ball pushing down on floor. If you ever want to jump, right, your legs will push down on the floor so that the floor will push your body up and then you can jump and do the slam dunk. If sports was still a thing, it's a COVID-19. Net force is 4.2. Yes. Yeah, 4.2. So what we want is not the net force, it's the force in the board. Go and try that May, June 18 question. Did I write the time? Did I write the date? Go try this one. May, June 18, paper 2-3, question 3. After this. You understand this one? You go take a nap, come back, try again. Make sure the ideas are correct. It's not so much that things will come out word for word. They will mix things up. You think about the big giant mind map I drew for the first 1 hour of today. They can mix things up however they want. It's like a buffet. They can choose their own question, build your own salad. So understand the ideas.